Exam 3 is Friday. I think that's 4-4. And the topics go up through, so through torsion with circular cross sections. So the stuff that I'm going to introduce today isn't on there. And the numbers of relevant practice problems are listed on D2L. They're all on the second set of practice problems. I think it's like 1 through 5. They jump around a little. It's 1 through 5, I think 8 and 9, and then 13 or something. But those are the topics that are going to be covered. And so today, what we've talked about for torsion is how to calculate the stress due to torsion with a circular cross-section. And we did that for a solid circular cross-section and for a hollow circular cross-section. Now we're going to talk about hollow shapes that aren't circular as long as the walls are thin. So what we're going to be doing is an approximation that gets better as the walls get thinner compared to like the overall dimensions of the cross-section. I want to do one thing. So the first thing I want to do is just talk about how to calculate the amount of torsion at a specific point. And you'll see that this really is pretty similar to internal loads problems. So what if you had a problem, so this thing, you have this column, and let's say that there's a torsion going this way of 10,000 Newton meters. And then let's say here there's a torsion going this way of 3,000 Newton meters. And then here there's a torsion going this way of 2,500 Newton meters. And say we want to calculate the amount of torsion here, here, and here. Okay, so how would you do that? Yeah, exactly. So what's the torsion at A, B, and C? So for A, let's do all the cuts from the top because we know the external load there. So we know we have a 10,000 Newton meter couple this direction at the top. And then we know that there's like some internal couple that's counteracting that. I'll call that T or TA. Okay. And you know that rotational Newton's second law, if we're doing the calculation about the long axis of this column, says, well, we have to choose a positive axis. I guess let's call that positive. So then we have positive 10,000 plus TA is equal to 0. So TA is equal to negative 10,000 Newton meters. Okay, and then that torsion, this TA is what you would use if you were trying to calculate the shear stress occurring at the point A. Okay. Any questions about that? Okay, so let's go on to B. So now we have a couple of 10,000 Newton meters there. And we also have a couple of 3,000 Newton meters there. Call that the positive direction. And then we have this couple TB that's applied by the rest of the body. So the rotational equation says positive 10,000. Well, I wrote this as 30,000, but the 3,000 Newton meter couple is going in the opposite direction. Oh, change this in these drawings. These should all be couples, so they all should have those double arrows. So 10,000 Newton meters minus 3,000 Newton meters plus TB equals 0. So TB is equal to negative 7,000. Okay. So if you were calculating the shear stresses due to torsion at A and B, you'd have different values for the torsion that you'd use at each of those. You'd use the negative 10,000 at A and you'd use the negative 7,000 at B. And then for C, you have 10,000 that way, 3,000 that way. Yep. And then 2,500 this way. TC. So 10,000 minus 3,000 plus 2,500 plus TC equals 0. So TC is equal to, what, negative 9,500? And notice that these internal torsions are what you use to calculate the shear stresses. So like, for example, in this formula, okay, this would be that internal torsion. Okay. All right, so now let's go on to thin-walled tubes. When the walls of the cross section are thin compared to the overall dimensions, we can calculate the shear stress for even non-circular cross sections. So for example, we can do this. this is the one that we could have done already, but we can also do this. And on this one, notice that the thickness in this drawing varies around the perimeter. We can do rectangular shapes. And we can do shapes that are totally asymmetrical. We can only do shapes, though, that have a closed thin wall. So the thin wall cross-section must be a closed shape so you can't use this for one example that maybe we'd like to be able to do this for would be like an I-beam. That's not a closed shape, so we can't do it. It also wouldn't work for something like this. Okay, because you have that break there. So we can't do either of these. As far as the tricky part of this calculation, you have to do that rotation of the coordinate system the same way we did with circular cross sections. So the tricky part of doing calculations like this is the same as the tricky part of doing it with circular cross sections. Okay. So for thin-walled closed tubes, the maximum shear stress is equal to the torsion over 2 times T times A sub M. And I'll tell you what all these variables mean. So T is that internal torsion. Little t is the thickness at your desired point. So in other words, if you look back at these two shapes where I drew thicknesses that vary as you go around the perimeter, if you're trying to calculate, say you're trying to calculate the shear stress here, you're going to use a different value of lowercase t than you're going to if you're calculating the shear stress here. Okay, so you're going to get different shear stress values at different points if the thickness is varying. And then A sub M is the thickness, it's the area of the cross section using the median of the wall. So for example, if you had a shape like this, if this is your cross section, then the area that you want, you just go like define a curve that goes through the middle of the wall the whole way around, and then this is the area that you want. And you can imagine if that wall gets thin, which, you know, our results are better the thinner the wall is, worrying too much about calculating that median just isn't a very big deal, because imagine, like, if this wall gets thinner and thinner, that A sub m ends up being about the same as the area at the outer wall and about the same as the area at the inner wall. Okay, so don't waste too much effort figuring out the median of those. Okay. All right, so let's do a calculation. And actually, for this, the calculation that I would like to do, we don't get the chance to do this very often. Like, there aren't very many cases in this class where we have multiple approaches to a single problem. But if we do a problem with a thin-walled circular cross-section, we can do it using the circular cross-section approach, and we can do it using the thin-walled approach. And we can see how good this approximation is. And we can, you know, sort of see where it's weak, where it's strong. So, okay, let's do this. Let's say that we have a circular cross-section with a coordinate system like this, x going down the long axis, y up, z coming out towards us. And let's say that there's a torsion on this side of 15,000 Newton meters. And let's calculate, so at the middle of this thing, let's calculate the shear stress at 2 points. First, A here, and second, B here. And the cross-section, I'll give you the dimensions. So let's say that the outer radius is 0.4, and the inner radius is 0.35. And we want to calculate the stress tensor at, I guess, yeah, let's do it this way. So let's calculate the stress tensor at A and the stress tensor at B. First, using the circular cross-section approach. And then second, using the thin-walled approach. And we want to see how close these are. You know, notice I didn't choose a shape that has a real thin cross-section compared to, say, the diameter or something. If you compare the thickness, well, let's do it as thickness to radius. What do you get? 0.05 divided by 0.4, so an eighth. So about 0.125, right? The thickness is about 12.5% of the radius. So we're going to see that this gives reasonably good results and sort of shows us that we don't have to be, it doesn't have to be too thin-walled compared to the overall dimension, but about 10% might be an okay rule of thumb, okay? Thickness over radius should be about 10%. So I'll do it as thickness over length. You can sort of define length however you want. This isn't a precise thing, it's just sort of a rough rule of thumb. Okay, so for the circular approach, well, the first thing we have to do is we have to know what torsion is at this point in along the length. So what's it going to be? What's the internal torsion at those 2 points? Yeah. So there are no other torsions anywhere along it. And we're ignoring weight, by the way. Okay, so the torsion is equal to 15,000. And is it positive or negative? Well, it's positive on the right side, but I never even really defined positive or negative because it doesn't matter. Remember, we're going to get our directions are all going to come from thinking about the deformation of that rectangle, remember? So we're going to use it as positive, and besides that, we don't really care. So what else do we need to calculate the shear stress? We're doing this using the approach that's going to be on the test, if that makes it any more interesting for part A. Yeah, right. We need to know the rho. So let me write this formula. So we're going to have the torsion times rho over the polar moment of inertia. Rho for the point A is going to be 0.4. And rho for the point B is going to be 0.35. And now we need to calculate the polar moment of inertia. So I sub p is equal to pi over 2 times the outer radius to the fourth minus the inner radius to the fourth. And you get 0.0166, probably sixes. I have 4 here. Okay, so the maximum shear stress is going to be 15,000. Well, let me write it like this. So we're going to calculate these two shear stresses separately. So let's first do it for A. 15,000 times 0.4 divided by 0.01664 and you get a value of 3.61 times 10 to the 5th pascals. So now, if you think of a rectangle surrounding this point, what's the direction of deformation of that rectangle? So the rectangle is going to be oriented like this with the coordinate system. There's x, y, z coming out. With a torsion like this, is the left or the right side going to be down? The right side's going to be down, the left side's going to be up. So we're going to get something like this. And that means that the shear stress is oriented this way. And so what element is that first? What element of stress is that? XY, yep, it's on the positive X face, parallel to the Y. And is it positive or negative? Negative because it's in the negative Y direction. So the shear stress, or well, the stress tensor at the point A is going to be 0, negative 3.61 times 10 to the 5th, 0. Then you have the symmetry, so negative 3.61 times 10 to the 5th there, and the rest are zeros. And do we have to rotate this to get it into our desired coordinate system? Nope. Okay, so now we have to do the point B. So the shear stress at B is the torsion, 15,000, times the rho vector at B, the magnitude of rho. Rho for B is going to be 0.35 because we're just going to the inner wall. So 0.35 divided by the polar moment of inertia. That doesn't change. That represents the whole cross section. So that is still 0.01664. And you get a value of 3.16 times 10 to the 5th pascals. So if you represent that point with a rectangle with the coordinate system like this, what's the deformation that's going to happen to this rectangle? It's going to be the same because that whole, all of the material in that tube is going to, the right side is going to do this side is going to do that, right? So that means that the rectangle is going to do the same thing, and the sign is going to be the same, the element is going to be the same. So it's going to go to this shape. That means the stress is in that direction. And so the stress tensor at the point B is equal to 0, negative 3.16 times 10 to the 5th, 0, negative 3.16 times 10 to the 5th, 0, 0, and zeros on the bottom row. Okay, well, one thing that you notice is that the stress tensors are different on the inside and outside of the wall. Using that torsion formula, so look back at that torsion formula for thin-walled shapes. There's nothing in this representing different points along the thickness of the wall. Okay, there's a thickness here, but both of these points A and B are on the same part of the wall, so that T value is going to be the same for A and B. Okay, and so basically when we use the thin-walled approach, we're going to approximate this case where we have different stress values on the inside and the outside by kind of an average of those two. Okay. So that's one reason why the better the thinner the wall is, the better your approximation is. As that wall got thinner, these two values would start to approach each other. Okay. Okay, so now thin-walled approach. Okay, so the torsion, or the shear stress is equal to the torsion divided by 2 times the thickness times the area at the median. The torsion is 15,000. The thickness is 0.05 meters. The area at the median is pi r squared. And what's r going to be if it's the median of that circular shape? Yep, 0.375 squared. And so you get a value of 0.442 meters squared. So the shear stress is equal to 15,000 divided by 2 times 0.05 times 0.442, and you get 3.39 times 10 to the 5th pascals. And now you have to think about the directions again. So we've already done this, but this is what you would have to do if if you hadn't already done that other approach. So here's the coordinate system. And what's the deformation of this rectangle going to look like? The right side is going to be down, left side is going to be up. And so we have a shear stress on the x face parallel to y in the negative y direction. And so the stress tensor at A is equal to the stress tensor at B according to this approximation. And that's 0, negative 3.39 times 10 to the 5th, 0, negative 3.39 times 10 to the 5th, 0, 0, 0, 0, 0. Okay? So notice that this approximate value, where we treated both of those 2 points the same, had a value that was in between our two more carefully calculated points. Okay, so let's do one now. Let's do the same problem. But let's do it at this point, where this angle is 30 degrees. So use the thin-walled approximation. And we want to calculate this in this coordinate system. So y is pointing up, z is pointing that way, x is coming out at us. Okay, so if you use what we've already done smartly, you can actually use the stress tensor we just calculated and just do this as a single rotation. So see if you can figure out how to do this. Compare answers to each other. It should only take a couple of minutes.